Okay, let's start lecture. This last lecture, we will introduce one of the most used models in probability, which are Bernoulli trials. Essentially, we already did them. In the case of two Bernoulli trials, what are Bernoulli trials? Are simply coin tosses. I mean, I say coin tosses, but I mean, yes. Let's think about just about coin tosses. So I will say how they're applied later. But by now, let's think about coin tosses. So the sample space is equal to 0, 0, 0, 1, 1, 0, 1, 1, where each digit is heads or tails, means, and the position of the digit is related to the coin toss. The first digit is related to the first coin toss, and the second digit is related to the second coin toss. So 0, 0 is, for example, the first digit. The first coin toss is 0, is tails, and the second is tails. To write it more mathematical, in a mathematical way, omega is the set of strings of two digits, where each digit is 0 or 1. We want to do independent trials. And first of all, we toss two identical coins of success parameter P, which is a number between 0 and 1. What does it mean, success parameter? Well, it's the probability of having a heads. In the language of coins, a heads is a success and a tails is a failure. So let's put this in a mathematical rigorous way and define x1, which is equal to 1 if the first coin is heads, 0 otherwise. x2, the same variable, 1, but related to the second coin. If the second coin is heads, 0 otherwise. Once again, we can, for example, we want to compute the probability of 1, 0. How the first coin is 1 gives heads and the second tails. We can write this event as x1 is equal to 1, the first digit is equal to 1, and x2 equal to 0, the second digit is equal to 0. Well, once again, we multiply and divide by x1 equal to 1, so that we will make appear a conditional probability, and this is equal to the probability that the second coin gives 0, given that the first one is 1, times the probability that x1 is 1. Okay, we can now use the independence. In this case, what does it mean? Means precisely that x2 equal to 0, that the second coin is tails, given x1 is equal to 1, is equal to the probability that x1 is equal to 1. Okay, and this is exactly the same. So the independence implies that the probability of 1, 0 is equal to the probability of x2 is equal to 0, given that x1 is equal to 1, times the probability that x1 is equal to 1, it is equal to the product of the probabilities. Okay, this is the independence hypothesis. Now, we use the hypothesis of hypothesis on the coin is that the success parameter, the coins are identical, and the success parameter is P. In coins is that the probability of x1 being equal to 1 is equal to P. And for instance, the probability of x2 equal to 0 is equal to 1 minus P. For example, so that continuing with this, substituting these values here, so that we can substitute those values here, and this is the probability of 1, 0 of seeing a heads and then a tails. Of seeing heads and then tails. Sorry. Then, okay, we can do these computations for every x1, x2 element of omega. How do we write this? x1, x2 is equal to the event x1 is equal to capital X1 is equal to little x1, capital X2 is equal to little x2. So we can continue and write probability of x1, x2 is equal to the probability x2, x1, capital X1 is equal to x1, and capital X2 is equal to x2. Recall that capital X is the result of the first of the coin toss, while x1 is a little x1 is a fixed number in 0, 1. Okay, and this is equal to the probability that x2 is equal, capital X2 is equal to x2, given that x1 is equal to little x1 times the probability of x1, capital X1 equal to little x1. Now, what does the independence hypothesis tells us? What does the independence hypothesis tell us? Well, it tells us that the probability of x2 being equal to little x2, given that x1 is equal to little x1, this is equal for each capital X1, capital X2, cioè little x1, little x2 in 0, 1, this is equal to the probability that x2 is equal to x2. Capital X2 is equal to x2. So using the independence hypothesis, in general, the probability of x1, x2, it is equal to the probability of capital X1 is equal to little x1 times the probability of capital X2 is equal to x2, little x2. Okay. This is what we did it in the last lecture, the previous lecture. Now we want to use a smart notation. This is just a notation. Not a notation, it is an equality. Let's see. To the probability that, let's say, the first coin toss is equal to little x1, where x1, little x1 is a number, which is either 0 or 1. This is equal to p if x1 is equal to 1. This is by definition, the coin has success probability p. And it is 1 minus p if it has probability 1 minus p to give tails, this coin. Okay, we want to rewrite this expression. Okay, let's see, for example, p to the power x1 times 1 minus p to the power 1 minus x1. Well, let's say, if x1 is equal to 1, well, p to the power 1 is equal to p. 1 minus p to the power 0 is 1. So, you see that if little x1 is equal to 1, this left-hand expression on the left-hand side is equal to p. While if we substitute x1 equal to 0, p to the power 0 is 1, and 1 minus p to the power 1 is 1 minus p. So this is equal to 1 minus p, which is exactly as the above expression. So we can write the probability of x1 equal to capital X1 equal to x1 as p to the power x1 times 1 minus p to the power 1 minus x1. To check this equality, just substitute the values x1 equal to 1 or x1 equal to 0. Okay, but now we know that the probability x1, x2 is equal to the product because of the independence, and now we substitute this expression here. We recall that the coins are identical. So the p is the same. So we have that p, this is equal to p to the power x1 times 1 minus p to the power 1 minus x1 from this left, the first factor. And the second factor is simply, instead of x1, we put an x2. The probability that the second coin as result x2 is equal to p to the power x2 times 1 minus p to the power 1 minus x2. And this is equal to p to the power x1 plus x2 times 1 minus p to the power 2 minus x1 plus x2. Okay. And this is the Bernoulli, the measure of the Bernoulli trials, the probability of two Bernoulli trials, parameter p. Observe that if p is equal to 1/2, then the probability of x1, x2 is equal to 1/4 for each x1, x2. Each outcome is equally likely because, well, this you can check it. It's easy to see. We can do the same reasonings on 3 coin tosses. So that here omega is equal to 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. up until 1, 1, 1, which is equal to the strings, the set of strings of 3 digits where each digit is in either 0 or 1. We can do the same. Well, we're doing Bernoulli, we're tossing 3 coins independently, each of which, so toss of 3 coins. The toss of 3 coins tells us that we have this sample space. This. Then we toss 3 coins, which are of success parameter identical of success parameter P. What does it mean, this? So toss of 3 coins means that omega is that one. Of success parameter P means that if we define the probability of x1, if we define x1, xi equal to 1, if the ith toss is heads, 0 otherwise, then the probability, sorry, this is a capital X, the probability that x1 is equal to 1 is equal to the probability of x2 equal to 1, which is equal to the probability of x3 equal to 1, which is equal to p. So the probability that each coin separately gives heads is p. So we have then 3 coins of success parameter p are thrown independently. We will see later what is the independence hypothesis, but by now we have used the 2 data. Okay, well, we can do, for example, the same computation as above. For example, the probability of a given triple of a given result x1, x2, x3. This is equal to the probability that capital X3, recall that x1, x2, and x3 are just either 0 or 1. Okay, we are writing the generic element of omega, the general outcome. So this is equal to the probability that x1 is equal to capital X1 is equal to x1, and the probability that and x2 is equal to little x2, and the third digit is equal to x3. And now we again multiply and divide as we did before. This is equal to the probability that the third digit is little x3, given that the second one is equal to little x2, and the first one is equal to little x1, times the probability that x2 is equal to little x2, the second digit is equal to little x2, given that the first one is little x1, and the third, the probability that the first digit is little x1. Okay, now we can use the hypothesis of independence. What does it tell in this case for 3 Bernoulli trials? Independence the independence hypothesis is that the third digit, the third coin toss, does not, the probability of the third coin toss is not influenced by the probability of the first two. So this is a first. This is the first hypothesis, and then the second, no, this is the one, the mathematical formulation of independence is this two set of equalities, this set of two equalities, which is x3, that the third coin toss, given the first two, has the same probability of, is not, the probability of the third coin toss is not influenced by the realization of the other two, the two other tosses, and that the probability of the second toss is not influenced by the probability of the first one, by the appearance, by the occurrence of the first toss, coin toss. Okay, so if we use the independence, which are those two equalities, then the probability of x1, x2, x3 is equal to the product of capital X1 is equal to x1, capital X2 is equal to x2, capital X3 is equal to x3. And this, once again, we use the same equality as before, is that the probability that xi is equal to little xi is equal to p to the power of xi times 1 minus p to the power 1 minus xi. Once again, why is this true? Well, we simply see that this is equal to, we substitute xi, recall that xi is either 0 or 1. So if xi is 1, 1 minus xi is 0, and whatever number to the power of 0 is 1. So this is equal to p to the power 1 times 1. If xi is 0, then p to the power 0 is 1, 1 minus p to the power 1 is 1 minus p. So you see that this is exactly the expression, the probability of a coin having, it is 1 with probability p and 0 with probability 1 minus p. Substituting those values here, and this is the hypothesis on the coin probabilities, on the single coin probabilities. This is equal. So this is due to independence. And this is due to the hypothesis on the coin. Of being a coin with success parameter p. So this is equal to p to the power x1 times 1 minus p to the power 1 minus x1 times p to the power x2 times 1 minus p to the power 1 minus x2 times p to the power x3 times 1 minus p to the power 1 minus x3. And this is equal to p to the power x1 plus x2 plus x3 times 1 minus p to the power 3 minus x1 plus x2 plus x3. And this is the probability of 3 Bernoulli, independent Bernoulli trials. Okay, I give you an exercise, and let's say that this is a exercise. Okay, no, let's do this in lecture. So the exercise is define h equal to the number of heads in 3 Bernoulli trials. Compute the probability of h being equal to 0, the probability of h being equal to 1, the probability of h being equal to 2, and the probability of h being equal to 3. Compute these 3 probabilities. We have 10 minutes to do this. And I will continue this registration and correct it. Okay. Let's say I correct only these two, the probability of these two events, h equal to 0 and the event h equal to 1. H equal to 0 is the event 0, 0, 0. H equal to 1 is the event 0, 0, 1, 0, 1, 0, 1, 0, 0. Well, the first one, the probability of h equal to 0 is equal to the probability of 0, 0, 0. Okay, we go up and see the probability. The probability, so recall. Probability of x1, x2, x3 is equal to p to the power x1 plus x2 plus x3 times 1 minus p to the power 3 minus x1 plus x2 plus x3. Well, if x1, x2, x3 are 0, this is equal to p to the power of 0 times 1 minus p to the power of 3 minus 0, which is equal to 1 minus p to the power of 3. Okay? You can check that the probability of h equal to 3 is equal to the probability of 1, 1, 1, which is equal to p to the power of 3. Let's now compute the probability of h equal to 1. This is equal to the probability of 0, 0, 1 of the elementary events that compose it. So 0, 0, 1, 0, 1, 0 plus the probability of 1, 0, 0. Okay, let's look at the probability, for instance, of 0, 0, 1. This is equal to p to the power x1 plus x2 plus x3. This is in general. Sorry, doesn't work. My tablet doesn't work. Okay, yes, now it works. Okay, we have to substitute x1 equal to x2 equal to 0 and x3 is equal to 1. So this is equal to p to the power 0 plus 0 plus 1 times 1 minus p, 3 minus 0 plus 0 plus 1, which is equal to p to the power 1 minus p squared. So a success plus 2 times 2 unsuccess. This is quite intuitive. So you just multiply p, the number of 1 times, and then 1 minus p, the number of 0, the same number as 0, as the same number as many zeros are in the string. Okay. So the probability of 0, 1, 0 will be the same because there is also only a success. And it will be so that this expression will be the same. You have only to change. It depends only, you see, depends only on the number of ones. Okay, so this is equal to p to 1 minus p squared, which is also equal to p to the power 100, p of 100, so that the probability of h being equal to 1 is equal to p times 1 minus p squared plus p times 1 minus p squared plus p times 1 minus p squared, which is equal to 3 times p times 1 minus p squared. Okay, you can do h equal to, but observe that the probability of x1, x2, x3 is equal to p to x1 plus x2 plus x3 times 1 minus p to the power 3 minus x1 plus x2 plus x3. And this is equal to p to the numbers of ones times 1 minus p to the number of zeros. So you see, you have to multiply p times the number of successes and 1 minus p, the number of unsuccesses, of failures. So in a way, every string which has the same number of ones has the same probability. So and this makes this is something you have to keep in mind. If we have time, we will introduce the binomial distribution, which will be exactly the number of heads on in a Bernoulli trials. And we use this fact that the probability of a elementary event depends only on the number of ones. Okay. We can do this in general. I don't know how worth it is, but let's do it. And then maybe we will introduce rapidly what is a random variable and introduce only the binomial random variable. And then we stop because it's already a nice. We didn't. We can say that we did something. So, in general, and Bernoulli independent trials. we usually, as usual, omega, we toss n coins. The space of n tossed coins is the space of strings of n digits, where each digit can be either 0 or 1. And okay. This is the space of n coin tosses. Then we define xi equal to 1 if the ith coin gave heads, 0 otherwise. And we do the same computation as before. As the fact that the coins are identical means that the probability that the coin the ith coin is equal to xi is equal to p if xi is equal to 1. 1 minus p if xi is equal to 0. And this is equal to p to the power xi times 1 minus p to the power 1 minus xi. Well, once again, to write the probability of a string, an outcome of n coin tosses, this is the probability that x1 is equal to capital X1 is equal to little x1 and etc xn is equal to little xn. And now we can usually multiply and divide. So this is equal to the probability of x1 equal to x little x1 and etc and xn equal to xn. Then we divide by the probability of x1 equal to x1 and etc until xn minus 1 is equal to xn minus 1. And we multiply for the same thing times the same thing. And we divide again, taking off one of the variables until we arrive to etc to the probability of x2 equal to x2 and x1 equal to x1 divided, and we divide and multiply by the probability of x1 is equal to little x1 times the probability of x1 is equal to little x1. So that this is equal to the probability of xn being equal to little xn, given that x1 is equal to little x1 and etc and xn minus 1 is equal to little xn minus 1. etc times the probability of x2 is equal to little x2 given that x1 is equal to x1 times the probability of x1 is equal to x1. This has the usual interpretation. We toss the first coin and it gives you x1. What was the probability of that? Okay. Then we know that the first coin gave x1 and we toss the second. Then we know that the second and the first one have that result, and we toss the third one until we toss the last of them, which is this one, knowing the past tosses. Okay, this is so it's very intuitive, this formula. And now we use the hypothesis of independence. Now it's the hypothesis of independence of an event is this one, that if we know that the probability that x1 xn minus 1 equal to xn minus 1 happened, the past tosses don't change the probability of the toss xn. Etc., and the probability that x2 is equal to little x2 given the first toss doesn't change. This is again the probability of x2 being little x2. Okay, this is are the hypotheses of independence. We plug in the probability in the above inequality, the above equality, to obtain that the probability of x1 xn, which is equal to the probability of xn being equal to little xn, given that capital X1 is equal to x1 and etc. xn minus 1 is equal to little xn minus 1. This is equal to the probability, no, sorry, times etc. times probability of x2 being equal to little x2 times the probability of x1 being equal to little x1. We recall that xi is in 0, 1, and capital X is the result, so that capital X I being equal to little xi is like the result of the I coin toss is little xi. Xi is 1 is the event, the result of the I toss coin, toss the coin is equal to 1. Okay. So once again, we use the independence hypothesis, which are these ones here, to say that this is equal just to the product. Which is equal. We use now the hypothesis on the coin to p to the power x1 times 1 minus p to the power 1 minus x1 times p to the power x2 times 1 minus p to 1 minus to the power 1 minus x2 times p to the power xn times 1 minus p to the power 1 minus xn. This is again equal to the probability of x1 plus etc. plus xn times 1 minus p to n minus the probability of x1 plus etc. plus xn, which is equal to p to the number of ones. The number of ones of the string x1 xn times 1 minus p to the number of zeros. This is very intuitive because if there are, we multiply p when we saw a success, we multiply by p. When we saw a failure, the failure has probability 1 minus p, and they just multiply each other. This is due to independence, the fact that they multiply, you need just to multiply. And this is the probability measure we were looking for. We now, this is very important, just to make a little excursion of the hypothesis of independence. So we saw some cases of independent or dependent Bernoulli trials, and where the extractions of the exercise of the previous lecture of the ticket. You buy 3 tickets. When you buy, if the first one is winning, then the second one will have a probability, a smaller probability of being winning. So that is an example of dependent Bernoulli trials. Independent Bernoulli trials are often used to model like the failures in some fabric. Like a fabric has to create like a car, and the motor can have not usually you can have some errors, and P is the number like you think that those errors are independent one from another, and the number the history of errors will be given by Bernoulli trials. You see, okay, this car has it, will it break down soon because of an error? Has probabilities P. And there are some, I think that one the object of statistics, one of the exercises is to compute that parameter P for a certain industry, which like fabric some pieces, and you want to estimate this parameter P if I'm assuming this hypothesis, which is not true, it's just you have to of independence. Of course, it can be true to some extent, but you have to back up by data. So an exercise in statistics is to estimate this parameter P when like you can have errors in some industry that produces pieces. The pieces are good with probability 1 minus P, and are bad with probability P. Okay. Then another stuff that one can do is that, for example, if xi is not a coin toss, usually it isn't, because it would be very restrictive. If xi is like the weather of in day one, if the ith if the ith day is sunny, 0 otherwise. Of course, up until here, this formula is true for every definition of xi. We just multiplied and divided obvious definitions. So we didn't use any particular property of the xi. So this is always true. But so here you are conditioning on the all past history. With the weather interpretation, you are calculating the probability of being like sunny, that the day number n, let's do, okay, the day number n, it's sunny given that the first day was not sunny, the second was sunny, and yesterday was sunny. You can make a less restrictive hypothesis, which is called the Markov hypothesis, which is not independence, is Markov hypothesis is that the Bernoulli trial number n depends, the probability of the Bernoulli trial number n depends only on the Bernoulli trial of n minus 1. This makes sense if you consider the weather. I mean, the weather that will be if tomorrow will be sunny depends only on the if today is sunny or not. Does not depend if to the event that 3 days ago was sunny or not. because this is called a memory loss property, and usually is it's a property which simplifies a lot the above expression, and it's simply, let me write it, for the three Bernoulli trials will be that the probability x3 is equal to little x3, given that x1 is equal to little x1 and x2 is equal to little x2. This probability depends only on the past history of the tosses or the weather, as you wish to interpret it, depends only on the last toss or last day. So this is equal to the probability of capital X3 equal to X3, given that X2 is equal to X2. And you don't care anymore about this event. This event does not influence the probability, only this event, only the event. This is the Markov hypothesis, which can be read in general, takes this form. Probability that capital Xn equal to little xn, given that the past history of tosses or of weather, as you wish to interpret it, xn minus 1 equal to x1, xn minus 1. This is equal to the probability of xn equal to xn, given that xn minus 1 is equal to little xn minus 1, only on the weather that was there yesterday. And this is a sort of memory loss property. You see, it simplifies a lot the expression above, and the property, which is, of course, much more general than the independence hypothesis, and gives rise to the theory of Markov chains. Which I think that you will study at some point. Then one last thing about random variables, and then I stop. When the experiment is observing a number, that number, so if let's go back to where we started. If the events that you're observing are the result of a number, if x a number, a well-defined number, if x is a well-defined number, but you don't know the value, you are uncertain the value, then x is a random variable. Assume that you know that assume that for some reason you know that x takes values 0, 1, n, etc., etc. Examples of these numbers are x is equal to the number of days until your telephone breaks down, or can be x equal to the number of heads in n Bernoulli trials. So this is a number, a random number, and you don't know its value, but you know that it's well defined. This is like events. You don't know if they are true or false, but they are true or false. Either in this case, x has a value, and but you don't know which is it. In this case, you can do the elementary events if we assume that x can take only the values 0, 1 as the previous two random variables which I wrote. If you assume that it takes only the values 0, 1, 2 in the natural numbers, then the elementary events of observing a number are x equal to 0, x equal to 1, etc., x equal to n, all these events, and a probability in it, the probability defined on these elementary events, on this experiment of observing that random variable is called the distribution. So the distribution of x is the probability defined on omega equal to x equal 0, x equal 1, etc. in the sample space whose elements are the elementary events of observing the random variable x1, x equal to 0, x equal to 1, etc., etc., x equal to n, etc., etc. And the probability defined on these elementary events is called the distribution of x. This is as simple as that. With what we did right now in this course, you should be able just to understand what is a random variable, why when you consider two random variables, there can be correlations because you are like looking the two together. And I think that we have no time to treat this topic. And that's it. Okay, now let me finish with the random variable. So just a definition. If h is defined as the number of heads in n independent Bernoulli trials, of success parameter p, then the probability that h is equal to 0 is equal to 1 minus p to the power n, the probability that h is equal to I is equal to the binomial coefficient choose I over n times p to the power I times 1 minus p to n minus I. And the probability that h is equal to n is equal to p to the power n. Okay, this is what is called the binomial distribution. I didn't have time to say what is the binomial coefficient. I hope that if that you have seen it in school at school. If not, but I think that you will do. You will eventually introduce the binomial distribution, and of course you will see again what binomial coefficients are.